Okay, welcome. Can I say it's lovely to see so many familiar faces, but we never get a chance to talk. You know, life's very busy. So this is, I was going to just give the same talk I gave to 50 of the world's greatest thermometrists, but I thought, no, just change a few bits because otherwise it wouldn't make any sense to you. So, you know, time has moved on. We're on a different date. So I came up with this title, The Most Accurate Temperature Measurements Ever Made, probably, but then I failed to get sponsorship from Carling, and so I've switched to this title here. Every temperature measurement you make is wrong, but by how much? That's what we're going to talk about. Obviously, it's a very modern talk, so you do feel free to live tweet. Okay, so if you want to know what the temperature is, obviously you start with a thermometer. For those of you who don't know what one is, this is a thermometer. Please feel free to, it tells you the temperature at the end. Do pass it around.
You can tell them which end.
Play with it while I'm talking. Then what you do is you use a thermometer and you have it calibrated. Now, if you live on Earth, then what having it calibrated means is that you compare it against standards defined by the International Temperature Scale of 1990. And it is literally all over the Earth. It's a phenomenally successful agreement, and people are able to work out what the temperature is for all practical purposes using this. And there's an instrument that's central to the way people do it. It doesn't work for some of the high temperatures that Emma's going to talk about, but for the bulk of temperatures that people use, what having it calibrated means is that somebody will compare your thermometer with a standard platinum resistance thermometer, which is a device that has a coil of platinum wire in. And if you zoom in, some of them are incredibly beautiful. They're coiled coils. And it's appropriate because this is, if you like, the DNA of ultimate thermometry, in that this is behind every temperature measurement, somewhere along the line, there will be one of these devices. And I brought one down. This is a broken one. So obviously you can break it further. You can actually break the glass. This one just doesn't work. So what I'm going to do is just pass it around here. There's a magnifying glass here. This is just so you don't have to be bored by me going on and on. So that's the business end. Okay, so that's the SPRT, and it's central to the way we measure temperature. And so you might understand that we've worked out how the electrical resistance of platinum varies with temperature. That's what so we measure its electrical resistance and work out the temperature. And what we've done is worked out how the temperature, the resistance of platinum varies with temperature. And we've got two very high order polynomials. So over this region, over on the right, does that produce a laser? No. This region up on the right, we've got this polynomial. It's a 9th order polynomial. And on the region on the left, we've got this 12th order polynomial. So it's got lots of mathematics in, so it must be very exact. That's the main thing. But there are two questions about this graph. Even though it's fundamental to every temperature measurement, there are two interesting questions. So the first one is this. Why? You can see the line is pretty straight. Oh, I didn't do that. You can see the line is straight here, but why did we split it in the middle and have one polynomial here and a completely separate polynomial there? Why did we do that? And then the second one is, where did these numbers come from? I just told you that the way we calibrate a thermometer is to compare it with the reading you get from one of these thermometers. But how did someone calibrate the first one of these thermometers? Did it come with Moses on the back of a stone? The resistance ratio of platinum shall be. How did we work out where those numbers come from? Okay, we're doing okay for time so far. Is everyone relaxed? Any questions at that point? So, lights. Yes, thank you very much. So now that we're relaxed, is anything else, Susan? Okay, so what's special about that temperature? Well, that's the temperature of the triple point of water. So what? You see, I'm using a text thing to kind of let people get the sort of modern thing. So that temperature is 273.16 Kelvin exactly. So I have a glass cell here in which we have the triple point realized. It's a glass cell in which there is water, water vapor, and ice. And the temperature at the top probably was, just before I took it out, was about 273. It defined what we mean by 273.16 Kelvin. You get everything first, don't you? It's cold. So you can see all three phases of ice, of water together. So why is that important? Because this is how we define temperature measurements on Earth. We pick this temperature here, the temperature of the triple point of water that occurs just at that point in a triple point of water cell where solid water, ice, liquid water and water vapor all coexist. And every temperature measurement on Earth is a quantitative comparison of the temperature of the thing you're trying to measure with the temperature at just that point in a triple point of water cell. This is kind of arcane, but it's absolutely true. You're staring into the holy of holies of thermometry. Okay, so that's question one answer. Why is that a special temperature? So we've got a polynomial that relates temperatures above the temperature of the triple point of water and temperatures below the triple point of water, but the triple point of water, 273.16 Kelvin, is the focal temperature for thermometry. Oh, thank you very much. It's all going wrong, isn't it? There we go. So how can we work out? The second question is, where did those numbers come from along the bottom of the graph? In other words, how can we work out how much hotter or colder something is than the triple point of water? Well, you use what's called a primary thermometer. What's a primary thermometer? Well, what you do is you go to Wikipedia and it tells you a primary thermometer is a thermometer that measures a property that you understand so well that you can read out the temperature from the value of the property. Now, that doesn't include the electrical resistance of platinum. So if the resistance of platinum has doubled, we're not able to work out what that temperature is from first principles. It's just too complicated, the physics. But we can find physical systems that are very simple. And that's how we estimated the temperatures along the bottom of the graph and worked out how the resistance of platinum varies with temperature. So the numbers along the bottom here were originally primary temperature measurements. So each one would be a very complicated experiment. And so at this point, we summarize part one, and ITS-90 measurements are based on our knowledge of how the electrical resistivity of platinum varies with temperature. And we call temperatures estimated that way T subscript 90. Wikipedia says that primary thermometers are relatively complex, so it must be true. And it is absolutely correct in this case. And we call temperatures estimated using primary thermometers T. So, okay, so that's the first bit. Does anyone have any questions at this point? You're so quiet. Okay, so I'd like to tell you about acoustic thermometry. It's a technique of thermometry which is a primary method. It starts out with the motion of the molecules. They've got kinetic energy in each of three directions if you pick simple molecules. And so again, there's more maths, I'm sorry. So this is what we want to get a hold of to relate things to temperature. And it turns out that this quantity is directly related to the speed of sound. And so by measuring the speed of sound, in fact, it's the speed of sound in the limit of low pressure, when the molecules are very dilute, we can estimate the temperature. And so the way we can estimate temperatures that we don't know, different from the triple point of water, is by measuring the speed of sound at the two temperatures, and the ratio of the speed of sound squared is just equal to the ratio of the temperatures. It works like this. So if we have an unknown temperature, first we take our primary thermometer to the temperature of the triple point of water, and we measure the speed of sound squared. We've done that so often. We have to keep doing it. And then we go to an unknown temperature, and we measure the speed of sound squared. And then we say, from first principles, we believe that the speed of sound squared is proportional to temperature. And then we can estimate the unknown temperature. It's just equal to the temperature of the triple point of water multiplied by a ratio. And it's the ratio of the speeds squared. And that's how you work out primary temperatures, how you work out the temperature of something from first principles. Now, we use a beautiful resonator thingy. It looks like this. And we have a plastic replica of one here. So again, you can hold this to distract you from what I'm talking about. That's a plug that plugs in and out. And inside here, we excite acoustic resonances, just in the same way that an ocarina makes a beautiful sound when you blow over it. So this is really a sort of technical ocarina. So there's a formula that gives us the speed of sound in terms of things we can measure. So the first thing we measure is the resonant frequency, and we also measure the width of the resonance. And there are constants here that relate that resonant frequency to the speed of sound, eigenvalues. And there are lots of different resonances that we can measure. I would love to tell you how we measure the average radius, but it's a long story, and it's a story for another day. So here we measure this resonance, we measure the frequencies of the resonances. Just remember how these are very sharp. So this is 7.5 kilohertz, 7.5 kilohertz. This is 2 hertz for each square on there. And we measure the central frequency and the half width. And the width of the resonance comes from energy being dissipated in the resonator. And that happens mainly here in the boundary layer, where the sound wave interacts with the wall of the resonator. And there are two important things about acoustic thermometry that make it sweet. The first one is that we can measure how much more energy is being dissipated than we expect. And if there's anything happening inside the resonator that loses energy, then we'll detect it in the width of the resonance, and we can say, ha, something's happening, and investigate it further. And so checking that your half width is just what you think it is really limits how wrong you can be. And the second thing is that you can measure multiple resonances, and they've all got to agree on the speed of sound. Okay, any questions yet? The buzz is not building. Okay, everyone's quiet. It's a flat audience. So what I want to do is just tell you about previous results. So as soon as people has made the ITS 90, everyone relaxed. It was a big event in the world thermometry. Everyone relaxed. And then people went back to measuring primary temperatures and realized that ITS 90 was now wrong. So let me show you some of those results. So this was the first sign that something was wrong, paper from Moldova in NIST in 1999. He used this giant 180 millimeter diameter steel cylinder with argon gas in, and he worked out that he measured T minus T90, how wrong ITS 90 is. And so these are millikelvins, so that's a plus or minus 100th of a degree. Here's the triple point of water, and he measured 3 points here and 2 points here. And I'm just going to draw a line through them, which are going to be on other graphs so that you can relate one graph to another, like that. So that's what Moldova, the way he thought it was wrong. And you can see it's wrong in quite a funny way. Then Ewing and Trussler at University College did work. They used an aluminium resonator welded together. They used argon. And they got these results. So you can see they kind of follow the trend a bit, but when you get below quite 100 degrees below the triple point of water. The things kind of curve back. Greg Strauss at NIST used Mike Moldover's resonator to make one more point. The team at INRIM used a stainless steel resonator, a very big one, again using argon gas, and they measured these temperatures. And again, you can see the same trends coming out. And Pitre, working at NIST, used a copper resonator, and he used argon and helium, very different gases, to measure T minus T90, and he got results that look like this. And again, you can see it's kind of following the trend, but just to draw your attention to this, one of those points was measured with helium gas in the resonator, and the other was measured with argon gas. And when you use the different gases, everything changes. I don't know if you've ever breathed in helium. Apparently you're not supposed to do it anymore, but acoustics changes when you use helium. And then finally, another team from NIST made some higher temperature measurements. And when you put them all together, you get this kind of trend. So we can now see a real trend building up for how wrong ITS 90 is. And when we looked at this at the consultative committee on thermometry, we recommended what we thought was the best guess for how wrong ITS 90 was. And we drew a line like that. The blue line was our best guess. And we put a spread on to just keep track of what was going on. So that's the International Bureau of Weights and Measures Consultative Committee on Thermometry Working Group 4. Okay, just to put this in context, for many of you who measure other quantities, so if you measure voltage, measuring to a part per million is no problem. If you measure lengths, typically parts per million, no problem. In thermometry, this is 1 part in 10 to the 5 of the temperature. So if you're inside that, then basically ITS 90, if you want to know the temperature to 1 part in 10 to the 5, ITS 90 isn't good enough for you, except right near the temperature of the triple point of water. If you're content knowing the temperature to 1 part in 10 to the 4, which most people are, then ITS 90 is good enough for you. But the labs that then calibrate your thermometers, it's not good enough for them. So we're trying to make, eventually we'll hope to make ITS 90 better. So now I can tell you about our results. We're building now. Can you feel the excitement in the room building? So here's our apparatus. So that's the copper version of that plastic thing that's going around. And inside here is a 124 millimeter inner diameter resonator, and it's filled with argon gas. I'll just show you some pictures of it. We made modifications from the last time we used it to measure the Boltzmann constant. And I really just want to show you these pictures of, this is the microphone, which is going through and is placed flush with the resonator on the inside surface of the resonator. And one of the things we did was move this is the preamplifier here, and it was previously directly bolted here, but that led to slight heating. When it was bolted on there, we found there was 92 microkelvins between the equator and the South Pole. So clearly we had to act. So now it's here, and now we can't detect any temperature gradients. And we also added extra thermometers. So here you can see we've got, these are ITS 90 thermometers that tell us what we think the ITS 90 is. Thank you very much. And inside, we're using acoustics to measure what the T, the thermodynamic true temperature is. Now we stick that apparatus in lots of different configurations. So first of all, we started out with a bath of antifreeze and we chilled it. And then we had a bath of ethanol. And then we had a bath of ethanol cooled with liquid nitrogen. And then we got rid of the ethanol when it turned to gloop, and cooled with liquid nitrogen directly, making arrangements on the top of the cryostat. And finally, we had this arrangement. So it's a long story of modifying the apparatus to get to the right temperatures. And now I'm going to show you some results. This is the exciting bit. Okay, so remember that inside there, we're measuring the speed of sound. And I want you to notice that thing, the resonant frequency divided by the eigenvalue, the constant for a resonance, is roughly proportional to the speed of sound. So here are some values for that. So first of all, you can see this is pressure along here, 5 atmospheres, 4, 3, 2, 1. So we're measuring down to about half an atmosphere. You can see at the temperature of the triple point of water, it doesn't vary very much with pressure. And we're trying to estimate this point over here. You can see as you go to lower temperatures, the frequencies go down. That's because it's a thermometer. The frequency, it's acoustic thermometer. The frequency is related to temperature. And you might think it would be easy to extrapolate those lines to get the zero value. But if you look in detail, you see it's not so easy. So I've blown that up now, and you can see every different resonance gives you a different value. But if you apply the corrections now for the half width, the loss mechanisms, what happens is that all those things magically come together in a way that's really sweet every time you do it. And you can now estimate where those are heading based on our understanding of argon gas. When you come to 253K, you can see the temperatures, the behavior is quite different now. But again, once you apply the corrections, you're able to extrapolate back to get a good estimate for the zero pressure speed of sound. And down here at 118 Kelvin, argon behaves very differently indeed. It's got a big pressure dependence now, and you might just be able to see when we apply the corrections, you should just see this come together. You see that just come together a little bit? So now we can estimate the pressure. So that's the data that we took, measuring frequencies. And when you put it all together to get estimates for T minus T90, you get this graph, which looks like that. And you see it's got, well, let's take a look at it. There's the crutches that I used to describe the previous data. And you can see this data really matches the crutches that I drew on the first graph. Now this is the curve that we drew in working group 4. And you can see now that what we thought was spread of the measurements in working group 4 is actually a real effect. That the data is not uncertain here, it's genuinely wiggling. And so there are just 2 points I want to make here. So one is concerning the behavior here near the triple point of water, and the other one here. So if we, do you remember this graph? Yes. Let's do it properly. Pretend you're at the pantomime. Do you remember this graph? Yes. Thank you very much. Okay, so, and the point here is, we're talking about this point here where we switch from one polynomial to the other. Now, these polynomials were constrained when they were made to agree with each other, but they weren't constrained to have exactly the same slope where they meet. And so we're looking at that point now, and people have been looking at this and drawing a line between these temperatures and these temperatures up here. And you can see there's a break in the slope of T minus T90. But we measured these points. So nobody had ever bothered to measure these points. And if you measure these points, you see actually there's quite a good match in the slope. And if there is a discontinuity, it's got the opposite sign to what people thought it was. So that's because we'd automated the experiment, we could take much more data. We could really investigate how this was changing. Now, the second point I want to make is about the wiggles. This curve here, these temperatures here, we estimated how the resistance of platinum varied with temperature based on primary thermometry prior to 1990, and we now know that was slightly wrong. And so what that does is the data we put on here was slightly wrong, and that slightly distorts the graph. So the error in primary measurements has distorted the slope, and I've tried to draw it sort of like this. If you imagine that this scale was slightly wrong, you'd get a slightly too steep a curve in some places and slightly too shallow a curve in others. And it's this that we're uncovering here when we're measuring the wiggles. These wiggles are real. We discover in the same way that Brian Cox and his friends are measuring echoes of the Big Bang, and they get ripples in space-time on the cosmic microwave background. So we're finding the ripples of ITS 90, the errors at the source, the origin of modern thermometry. Okay, so the summary is this. We've used closely spaced data. It's been very time consuming, but it reveals these wiggles. Our data is exceptionally good. This excess half width that I've mentioned but haven't had time to go into is the lowest that's ever been seen. And that's because we work with Cranfield University to make a really perfect resonator. We get an amazing agreement between the different acoustic modes that we used. So normally people have to compare a low frequency mode at one temperature with a low frequency mode at another temperature and work out the change in temperature from that, and then they do the same for different modes. For us, all the modes agreed with each other, so we could just use all the modes all together, and that reduced the complexity of our inferences and makes them more robust. And finally, we've got primary measurements of C0 squared, the speed of sound squared, and of temperature that are so good that the uncertainty in the primary measurement is probably better at some temperatures than the uncertainty in the ITS-90 measurement. That's the result. So there are just 2 slides more to show you now. The first is to say we're now going up to higher temperatures. We've bought a fan oven from hell, and we're going to put a resonator in there and take it up to 700 Celsius and see what happens. And the second thing is just this question of, does it matter? You might be thinking millikelvins, okay, it's kind of curious, it's kind of sweet, but who cares? And so this slide is for you, and it's just to point out to you again that if what I had told you about was that I was polishing a lens in order to make a sharper image, you wouldn't even ask me why I bothered to do it. You'd understand that having a sharper lens makes a sharper image, and then you can see things more clearly. Well, making precision physical measurements is exactly the same thing. When you measure things accurately, you bring the physical world into focus, and then you don't know what you're going to discover. Okay, thank you very much.